So, welcome everyone to the One World Combinatorics Onwards seminar. Our speaker today is Ignacio Mollo Cunningham from the University of Buenos Aires, and he's going to speak to us about is fully shuffling a rational operation?
Okay, thank you so much for having me. Uh, I'll start. Uh, I think it's always the polite and proper thing to do to introduce oneself. So I'm going to briefly say where I work and with whom. So I'm part of a research group in the University of Buenos Aires, which is called CAPAO, which its main interests are randomness, finite automata, and combinatorics on words. Uh, our leader is Veronica Becker. Maybe some of you have heard of her. And I'm right there. I'm a PhD student of Veronica, and my main interests are finite automata. Uh, But okay, that's a subject which is very related to combinatorics and words, and it was impossible uh, to get into it. And I'm slowly getting more familiar with it. So okay, let's start. Uh, my work is mainly concerned with the shuffling of words. I'm going to start by saying a few things that you all probably know already, but I'm going to go quickly into it. Uh, First, I'm going to define what is the shuffle of words. Given two words, we can define its shuffle to be a language which is comprised by all words that I'm sorry for the circularity, all words that can be obtained by shuffling the two words. And I'm using this notation, which, as far as I know, is due to Sakharovich. Uh, I've also seen the definition of the shuffle language of words as represented by a rotated E, but I always liked this notation more because it resembles a deck of cards being shuffled, and I always found it more suggestive than the other notation. Uh, of course, once you define the shuffle of two words, it's very easy to generalize the operation to the shuffle of two languages, which is simply defined as shuffling any word from one language with any word from the other language and taking union over everything. And a very well-known classical result is that if you take L and M to be regular languages, its shuffle will always and also be a regular language as well. And the proof is very simple. If you have a finite automaton for one of the languages and another finite automaton for the other, you can perform this sort of operation because the two words are like independent from each other. You can make sure that you can always make sure that you are reading one word from one of the languages and another word from the other language, and you can ensure that you can uh, realize the shuffle of them. But in my work, I encountered another context to think about shuffles of words, and I'm mainly I'm mainly thinking about shuffles of words as existing within a special monoid which I call the shuffling monoid. And the shuffling monoid contains triples of words, such that the third one is a shuffle of the first two. I'll usually call the third coordinate the output, and the words that are shuffled the input, left and right inputs. Unlike the definition I had given before, within the shuffling monoid, you don't forget what are the words that you are shuffling. So, for instance, an element of the shuffling monoid is the one that's in screen, AABB, ABAB. The third coordinate is obviously a shuffle of the first two. This obviously generalizes, and you have weirder stuff, but the main idea is that within this monoid, you don't forget what are the words you are shuffling. So, for instance, cara and lave can be shuffled to form calavera. Cara and lave cannot be shuffled to form caverala. And okay, yes, there's a lot of examples. And well, something I should say: this is a monoid with the pointwise concatenation, and it makes sense it works like that because concatenation is just the most boring way to shuffle words that there is. Okay, so it's really not hard to see that the shuffling monoid is generated by the following set of elements. By the way, just in case, I'm using epsilon for the empty word. So basically, because you know that you are shuffling the left and right inputs to obtain the output, you know that whichever you project on the output, you are getting it either from the left tape or the right tape, left inputs and right inputs. So whatever you have inside the shuffling monoid, you can always generate it by just multiplying elements like this. So I'm just showing a few examples of this. As you can see, it can get quite unwieldy. So what I usually do, I represent these elements as special symbols. So I'm using an A with a line over it to represent the generating element, which has an A on the left tape and nothing on the right. And I'm using the symbol A with a line under it to represent the opposite, when you have an A on the right input and nothing on the left. And well, you can see here that, of course, there are some elements which admit different decompositions. And sometimes, as you can see in the third example here, it's not trivial to go from one to the other. Although sometimes something that it's always true is that whenever you have the same word on the left input and the right input, that will always commute. So that's a useful property to have in mind. So what are we doing with this shuffling monoid? Well, of course, I'm going to define shuffling automata. I'm going to define what a shuffler is. A shuffler, I can simply define it as an automaton over the shuffling monoid. And we are going to require that all its transitions are labeled by atomic elements of the generating set. And you, you can simply think of them as transducers, three-tape transducers, which shuffle the first and second tape onto the second one. For instance, in the screen, there's a very, very simple shuffler, which realizes a finite set. And I'm going to usually be using the compact notation, which is a lot more legible. And I'm just saying things you probably already know, but a successful computation in a shuffler is simply a path which goes from an initial state onto a final state. Initial states I represent it with an inward arrow, and final states I represent it with an outward arrow. Uh, this is another very simple shuffler which realizes a set which is slightly more complicated than the one I presented before. And the behavior of a shuffler is simply the set of elements of the shuffling monoid, which are labels of successful computations of the shuffler. And in that case, we say that the shuffler realizes that set. And finally, as it's usually done, we call rational the subsets of the shuffling monad which are realized by shufflers. Finite state shufflers, of course. So there's a lot of things that there's a lot of questions that you can formulate once you have an object like this. I've dabbled into many of them. Like there's the question of are these automata are shuffling relations decidable, for example? There's a lot of decidability questions you can ask, like maybe you wonder whether if you have two shufflers like this, you can decide their equivalency. But in this talk, which is more related to combinatorics on words, I'm going to tell you about a question we solved related to the expressibility of shufflers. In particular, we are going to analyze whether these automata are expressive enough to realize full shuffles of domains. So I'm going to first define what that is. You start with a set of pairs of words, D, which is a subset of A star times A star. And we define the full shuffle of the set to be what's on screen. Basically, you take all pairs in the domain and you add to this set each possible shuffle of each possible pair in the domain. So a full shuffle. That's obviously a subset of the shuffling monad. And what we are wondering is whether is it always rational to fully shuffle a domain D like this if these are sets that are expressible by shufflers or otherwise well if they are not. And the easiest way to go about this is by starting with very simple examples and ramp up. So first we have the case of recognizable domains, where you have the product between two regular languages. And it's really not hard to see that if you have something like this, the full shuffle will always be rational. Basically, because given that D1 and D2 are independent from each other, you can do a very, very similar construction to what you do in the classical case, where you are just shuffling two regular languages. But in this case, the only thing you have to do is to make sure to remember where each letter is coming from. So it's practically the same construction with an extra step. So this is by far the simplest case, but once you go beyond the recognizable set, things can get a little more tricky. For instance, let's start with the simplest non-recognizable set domain, which is the one on screen. It's simply a domain where the left and the right tapes contain the same word, the same unary word. And if you do that, you will, of course, have a rational full shuffle because there's exactly one way to shuffle a to the n with a to the n that results in a to the 2n, and it's very easy to track that. So in this case, we get a rational full shuffle. Um, but as soon as you ramp up the difficulty a little bit, things start failing. For instance, if you consider what looks to be a very similar case as the last one, uh, it turns out that the full domain, the full shuffle of this domain, is no longer a rational set. And a very easy way to see this is that when you consider the full shuffle of this domain and you project onto the third coordinate, you get the most stereotypical non-regular language. So this cannot be rational. But let's ramp complexity a little bit. Let's consider now the domain which contains the same word on the left and the right. But let's take a word which is a little more complex. That's just a to the n. Let's take ab to the n. And what happens now when one tries to fully shuffle this domain? Will that be realizable by an automaton? Uh, this one's harder. Spoiler, it's kind of surprising, but the answer is, I mean, at least it was surprising for me. The answer is that this will be indeed realizable by a shuffler. And the idea is not that complicated. The problem with shufflers and automata in general is that, as we know, they cannot count. So if you go and do, like, suppose you are trying to recognize the word AB, 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 AB many times, there's many ways to do that as a shuffler. One thing, the most naive thing you could do is like read as much as you can from the left tape and then read the same amount of letters from the right tape. You can do that. It's a very naive approach, but this won't be able to be realizable by a shuffler because, in order to read the same number of words from the right tape, you have to remember how much words you read on the left. The poor shuffler cannot do that. But maybe somebody can come and say, it's very silly what you're doing. Instead of doing that, you can just do it like this. It's exactly the same, and it bounds the amount of it uniformly bounds the amount of letters you need to remember. You just alternate one to the other, one to the other, one to the other. The same happens when you read any amount of letters this way, instead of doing a silly thing like reading a lot from the left and then the same amount from the right. You can just distribute it. And of course, this is not the only way AB to the n can be shuffled with AB to the n. There's, of course, more complicated possibilities. You can get something like this. And even if it looks like you're forced to, once you read the last A from the left tape and you read another A, okay, then you're forced to read from the right. And maybe if you think that you're forced to keep reading to the right, but that's wrong. That's also a silly way to do things. You could do something like this, which is exactly the same. And well, essentially, what's going to happen is that because you have the same word on both tapes, you will always be able to redistribute the work so that they are kind of doing similar amounts of work at the same time. And actually, here is a finite shuffler which realizes the full shuffle of AB star. It's quite nice. Uh, of course, AB star is only the simplest case, and a very surprising, at least for me, surprising result that we obtained is that if you start with any word at all, then the full shuffle of WW star is always rational in the shuffling monoid. Uh, in particular, you project on the third coordinate and you get that the language obtained by shuffling, self-shuffling W to the n with itself, ranging over n, that will always be a regular language of A star, which at the moment I found quite surprising. I'm still kind of surprised by it, particularly because this is a extremely fragile result. For instance, suppose to begin with that W features more than one symbol, because if W is just A to the n, then the full shuffle is almost trivial. Suppose that's not the case. Suppose W features more than one symbol. If that's the case, W star will never be rational. That's not too hard to prove. Uh, but it's kind of surprising that it breaks as soon as you add another W to the mix. Another quite shocking example of the fragility of the theorem is that if you take any symbol which is not contained in W, then you add one single instance of that symbol at the beginning, either of the left or the right tapes, that's enough to break the rationality of the full shuffle. That symbol contaminates absolutely everything. Well, maybe this example is a little bit more extreme, but if you consider the full shuffle of the identity relation, that's not rational at all. That's also not very hard to see. So now I'm going to give a brief sketch of what's the idea behind the proof of this theorem. We are going to explicitly build a finite shuffler which realizes the full shuffle of this particular domain. I'm going to show it. I'm going to show you how it's done, or at least how I did it. And I'm going to start by creating an infinite shuffler, which does the work, and we will proceed to a finite one. Uh, so we start by considering this system. Here, where we are working with W equal to ABC. Suppose you have two infinite tapes with infinite copies of ABC up and down. Suppose you have one pointer for each one of these tapes. And suppose you also have a threshold, which is this pointed line here. The threshold tells you up to what point the pointer should read, and it's going to start moving right as soon as a pointer breaks the threshold. So, for example, as soon you start reading from the upper tape, you read an A on the upper tape. Then you move across the threshold, and this system, what's trying to do, it's trying to make sure that you're reading the same amount of ABCs up and down. So now that you started to read one of the ABCs up, the system is saying, "Oh, okay, so I have to complete an ABC up by reading BC, and then I have to match it with an ABC before." So the system says, okay, I have two letters to read in the upper tape and three letters to read in the bottom tape. However, maybe the system will not read exactly what it thinks it will read. Maybe it will read more letters downstairs than it would have wanted to. And in that case, the threshold will keep moving forward and forward and forward. And you could potentially make the very silly thing that we were discussing earlier of reading a lot from one tape and after a long time compensating from the other. So that's the problem. You can, that's the problem. And this will give us, if we just consider the number of letters we have yet to read from the upper and bottom tapes, this will result in an infinite shuffler, which does the job. It does the job, but it's infinite. So it's not really what we are looking for, but it's an approximation. The shuffler in question, it's this one. Here I'm choosing to represent it in a particular way. By the way, the numbers we are seeing there correspond to these numbers here, these numbers that are looking at how many letters we have left to read on the upper and bottom tapes. And this results in this infinite automaton, which actually realizes exactly the full shuffle of ABC star. But again, this is infinite. Note here that many of the states are represented more than once. For instance, the initial and final state 00 here appears two times, but it's the same state. It's just represented like this for reasons of clarity and either say beauty. Like it's it's consistent. Look at the 00, for example. When you read an A on the left tape, you are going to the state 2-3 here as well. In the other instance of 00, when you read an A on the right tape, you are ending up on 3, 2 here as well. This automata is consistent, but it's infinite. Even if some states are repeated, if you just do that very silly thing and start over reading from one of the tapes by following this row, for example, the depth will grow and grow and grow and grow. And if you just move along a row or along a column, you just you never pass from through the same state twice. So this is actually an infinite automaton, even if some of the states represented or repeated. I mean, all of the states are repeated infinite times here. So, okay, here is when I got lazy. I gave up with ticks and I started drawing because it was easier. This is the same automaton, but for AB, not ABC. This is a little bit simpler. And the idea here is to find a subautomaton of this infinite beast, which actually does the same job. And actually, the automaton in question, or at least one of them, will be this one. It's a very small subautomaton. Actually, it's the same automaton I showed you earlier, but it's represented in a less clear way when you see it as a subautomaton of the infinite one, but it's exactly the same. And the idea is quite simple, actually. Of course, this automata in red actually represents a priority over the left tape. This automaton will always try to read from the left rather than from the right, if it's able to do that. On the contrary, the blue automaton that is represented here, its priority switch. It will always try to read from the right tape first, if it can. Of course, because they won't accept the full the same set. You can consider an ambidextrous automata which does the same thing. And how does the proof go? It's actually quite simple. I'm of course not going to give it all away here, but the idea is that because this infinite automata it's quite symmetrical with respect to the diagonals. Whenever you have a path which starts in the main diagonal, the one with the zeros, and then it comes back, whenever you have something like that, then okay, whatever you did that could be done in one direction, you can always do it in the other direction because it's the same word repeated over and over on the two tapes. So actually, I could have ended the talk maybe half an hour ago when I was telling you this idea that if you can do something silly like over reading from one tape and then over reading from the other, then you can redistribute the work more evenly. It's kind of the same, but seen as paths on a graph. If you have a path that, I mean, that's the idea. Anyway, you can always. Oh, sorry, this is in Spanish. This is like the reflection path. Whenever you begin and end a path over a certain diagonal of this finite automata, you're able to do a reflective path the other way around which makes things even, or at least evener, between the left and right types. And it just so happens that by using this reflex path, you are always able to transform a successful computation here in the infinite automata onto a successful computation that always remains in this within these boundaries. That's essentially the proof. And of course, you can take this result and say, okay, I don't care about remembering what words I'm shuffling. I just care about the shuffle. So you can project on the third coordinate, and you get a family of regular languages, which are obtained by shuffling the same by self shuffling a regular language. So it's quite surprising that those are regular at all. And considering how fragile the result is, I'm, I'm surprised. Of course, something else one is able to do is play around with what's your initial state and what's your final state. And if you do that, you can obtain that the same result holds when W and W2 are conjugate words. If you have something like this, you get that this full shuffle will always be rational, and in particular, the projection on the tricoordinate will be a regular language. And also, if you append prefixes of the word, again by changing the location of the final states, you can absorb some prefixes of the word. You do not necessarily need to end on a whole uh, on a whole word. So, what are things that we are going to keep trying to do from here on? Okay, so actually, I've been trying for a while to give a finite presentation of the shuffling monoid. I mean, not necessarily a finite, sorry, but a presentation of the finite monoid, of the shuffling monoid, which is sufficiently nice. A finitary, say, presentation of the shuffling monoid, which is harder than it looks like. I'm also trying to prove a FAT2 property for the shuffling monoid, which is basically a sort of stability condition of the monoid, which says, okay, if you have a transducer which realizes a shuffling relation, then I want to make sure that I can do that with a shuffler too. Also, more related to this work, we have a conjecture. We're trying to prove that the full shuffle of U V star will always be rational in the case where U and V are conjugate words. We're trying to prove that. Like we prove, of course, one of the corollaries is the other way around. If they are conjugate words, then the full shuffle of U V star will be rational. But we're trying to prove that that's the only case where they are. Until very recently, we were trying to prove also we were trying to decide the equivalence of this kind of automata. We managed to do that like maybe a week ago. This is very recent, alongside Luc Pasma, a French researcher I've been collaborating with. So thank you very much for listening. If you have any questions about this, or if you have any comment, or if you are interested in any of these. I'm open to questions. If you are interested in any of these, you can write me. Thank you.
Thank you very much, Ignacio.
No, thank
Hajime
you.
has a question.
Yeah, sure.
Thank you for nice talk. So I have a question from in some sense, from the beginning. If
Yes.
when you consider shuffler, so you assume sort of deterministic property.
The term you're asking. Sorry, I didn't hear very well. You're asking about
Deterministic.
deterministic.
Sorry. Yeah, yeah.
Okay. Yeah, we've defined deterministic shufflers. They do not have very nice properties, unfortunately, uh,
Mhm.
but they are nice enough. For instance, uh, I should say a deterministic shuffler, as we define them. I mean, as my because these shufflers I kind of inherited them. My PhD advisor Veronica worked with deterministic shufflers as a way to define a notion of independence between normal sequences. And a deterministic shuffler is one such that every state reads only from one of the tapes, and also when you project over that tape, that's a deterministic classical automaton. So you read from exactly one tape from each state, and also from that same tape, you do not read the same letter twice. That's a deterministic automaton. We proved that equivalence for deterministic shufflers is decidable. Sadly, they do not have very nice properties in general. Like, for instance, there's very silly finite sets that deterministic automata does not realize. They are not close by complementation, which is something you really should have for deterministic automaton. Uh, but yeah, we work with deterministic shufflers. These shufflers we found in this work they are not deterministic at all. I think no, because they each state can read from up to two different tapes.
So not
So
not not good to
no, no.
not good to. So maybe not to uh, closed under reserve. So maybe if read left from left to right and read from left to right to maybe reserved. So not to closed under so
Ah,
reversal. So sorry, reverse, not closed under
okay,
reversal.
reversal. That's that's a question I have not resolved. I have not resolved it yet. I wonder about it, but it's in my to do list actually. I'm not
Ah,
sure
ah,
if they are close under reversal. I'm sure they are not close under most operations. Deterministic shufflers are not close under union, intersection, complementation. Given the trend, I'm pretty sure they are not close on the reversal too. I have not checked it. I'm not sure. I think the answer is no, but I'm not sure yet. It's actually on my to-do list.
okay, so sorry for so interrupting your future
No, no,
work.
it's fine. It's fine. All questions you want to ask, it's fine.
Thank you.
No, thank
Uh,
you.
Christophe, you had a question? Oh, you're muted, Christophe.
That's it. Yes. Sorry. Thank you for the talk. I wonder if what is the generating function of the shuffling monoid? Perhaps it's an easy question, perhaps not. I don't know. You
Oh,
you see, you have a degree function on this monoid. You say it is graded, and then you can count the elements of a given degree, and then you take the sum, infinite sum, the series, generating series.
okay, yeah.
You
Yeah,
see what I mean?
I don't know. I haven't, maybe it's an easy question. I haven't thought about it.
I have
I
no
always,
idea. Is it rational, a rational function, for instance, or not? I have no idea.
oh, oh, I'm not
Uh,
sure, but it's a really nice question. I'll add it to my to-do list. I haven't thought about it actually.
so that was my question. Thank you.
No, no, thank you.
Alessandro?
Yeah, uh, perhaps a silly question. I don't know. You said about the language you defined as a third projection, the one that is the language of self shuffles of a word
Yes.
in W star. Um, that is a rational language because of your what you proved. And
Mhm.
that's the same thing as the language of shuffles of an even number of copies of W, right? Or am I wrong?
Mm.
I mean, considering self shuffles of words in W star, so self shuffles of like W square with W square is just any shuffle of 4 copies of W, no?
Mm.
So
Yes, I
if
think
that's
so.
right, and I assume it is, but I may be wrong, my question would be, what about the language of shuffles of any number of copies of W, not just even numbers? Do you know if that's a rational language in general, or do you have counterexamples?
Mm. That's a great question. I don't know.
Okay.
Yeah, I don't know.
Okay,
But
thank you.
it's a great question. I have to think about it. No, no, thank you. It's a great question.
Thanks.
Are there any other questions? If not, thank you again, Ignacio.